Leif an undergrad, who will talk about order and chaos in some deterministic, infinite, trigonometric product. This is joint work with Professor Kiesling.
My name is Leif Albert. Over the summer, I was working with Professor Kiesling on a problem that he was sent by Benoit Cloitre, which was based on a paper that Professor Kiesling gave January this year, actually, to the same room, about the function SQ of x equals the infinite sum of sine of x over n to the q. And in a paper, he was able to prove that you can find a closed form for the behavior of this, where you have SQ of x equals a cubed sine of x to the 1 over q plus an error term of the lesser power. And that's an explicit formula for a of q. Now, and this is how it looks like. You can see that it has an upward tilt, and there's in green, maybe you can see it, I hope you can see it. In green, that's a square root of x times some constant. You can see it approximates. And for much higher x, you can see it still fits very well for a root x curve. Now, Benoit Cloitre, a week after Kiesling gave his seminar here, he gave another seminar, and he spoke with Professor Kiesling about his paper and his seminar, and he said, well, I have another problem that I've been looking at, and so I was wondering if you might be interested in it. And when questioned, Cloitre said that he had studied this for no particular reason at all. So, we'll see. And he's defined PCL to be this function, where before we had a sum of a trigonometric, now we have a product of a trigonometric plus some other strange constants within. And he surmised that the log of this approximates a negative root x, where c is a positive constant, which is similar to the function that Professor Kiesling had, except we take the log of it. And if we look, the shape of it is similar. It has the erratic things, and this is a negative root x curve, and you see it does approximate. This is the ln of PCL. And for much higher x, we can see the root x still well approximates this with some erratic behavior. This is the PCL itself, that is without the ln, and you can see that if the ln of it is approximately a negative root x, then we would expect the function itself to be e to the negative root x, which is what is plotted in green here. And we can see that it does approximate it somewhat, but there are all these bumps as well. Now, so my first thought over the summer was, well, these two do look similar, so I want to see if I can compare them. Maybe they're just off by a phase shift or something. Well, they're not. So I tried to overlay them, and at the very start you can see they sort of are similar with an offset, but it very quickly diverges, and the only thing that seems to be similar about them is the fact that they have a root x string. So that's our departure from that problem. And now, so we looked at this Cloitre product, PCL, and we thought, well, why are these, maybe we can generalize it rather than just look at specific cases of these numbers. So we defined CLPQ to be the infinite product of 1 minus P.
More to the left.
Oh, all right.
Further.
CLPQ is the infinite product n ln n of 1 minus P plus P cosine x over n to the q. So in our case, the original PCL function, we had P to be 1/3 and Q to be 2. So here is a graph of a different generalized Cloitre function, where instead we take P to be 1/2 and keep Q as 2. And you can see that this looks very different than what we had before here. In particular, because it's possible for a term in the infinite product to be 0, then the entire infinite product would become 0, and we take the ln of that and we get a disaster, these spikes. And all these spikes occur at the pi times odd multiples of the square numbers. So when we get x over n squared within the cosine. So over the summer we worked on this problem to see if we can prove that there is some trend function, maybe something stronger for the Cloitre function, and we were able to prove that for all x, CLPQ of x is equal to e to some constant times x to the 1 over q plus an error term. And that error term is bounded by another x to the 1 over q plus 1, that is a lower power, where c is this integral, which we'll talk about later. This is equal to e to the c e q epsilon x 1 over q plus epsilon p q epsilon x.
And for the chronometer values, it's important. P and Q
Yes,
satisfies.
all this this theorem was only proven for p strictly between 0 and 1/2, and q bigger than 1/2. We had problems where if p is equal to 1/2, you saw with this graph before, we have these things where it can't really be bounded by a lower curve because we have these infinite spikes. So our proof does not extend to p beyond 1/2. Now, for proving this, our method is, for small x, we use the Maclaurin expansion on the infinite product. For large x, we split the sum into a finite and an infinite part, using a very clever splitting. And for the finite sum, we show this is just an error term, which can be ignored. For the infinite sum, first we create a Riemann integral approximation and show it evaluates to be a negative constant x to the 1 over q. Then we show that the difference between the infinite sum that we split and the Riemann integral approximation is bounded by an error term of the same order as the finite sum. And lastly,
When you say it evaluates, you mean when you take the log?
Sorry?
When you take the log?
Yeah, that's
Yes.
what
And then we just find a series that converges to our constant and show that that does exist. So for sufficiently small x, we have, for x between 0 and x cubed, the Maclaurin expansion of our ln of our product, which we can clearly show is as follows, which is less than kx to 1 over q plus 1, which is the error term that we want over there. For large x, we split in the following way. We choose a tau less than pi over 2. That's within the first quarter period of cosine. We split the sum at n sub q x over tau, which we define as this. So as follows, we split this into a finite sum and an infinite sum at those bounds. For a finite sum, we just take the lower bound of cosine, which is -1. So then this must be strictly less than that, or less than equal to. And from that, we just have sum over a constant term. You multiply the inside by what you're summing over. And this has a power which is less than equal to, for some k, x 1 over q plus 1, which is again our error term that we want. Now, for the infinite sum, we'll first do a Riemann approximation. As I said, since tau is less than pi over 2 for large x, any two consecutive x over n to the cube, or x to n plus 1 over q, will be within the first quarter period of cosine for n larger than our bound. If x over tau is fixed and n increases, then those two consecutive terms will grow closer and closer together. So then we can represent this by an increasingly better Riemann sum approximation as this integral. We perform a substitution of xi as equal to v to the negative qx, and we have as follows. And we also extract x to the 1 over q, which is good. Now, since q is bigger than 1/2, this term goes to infinity like kx to 1 over q plus 1. And because of that, we can replace the upper limit of integration with infinity and get a proper integral. And so we perform the integration. And this is what we call our constant CPQ. So we show that our Riemann approximation equals to what we required before for e to the negative CPQ x and 1 over q. Now, for the n for the infinite sum, we try and find a bounded difference between our infinite sum and the Riemann approximation that we created. First, we just take the integral and move it within the sum by changing the limits of integration. Now we use the mean value theorem. So for some v at sub n, which is between n and n plus 1, we can do as follows. We can just, again, get rid of this integral. And then we just use the fundamental theorem of calculus, where we have n equal to and so we just take the integral of this, which we showed before with the Riemann sum is this, which is less than or equal to p over 1 minus 2p, because we just use that cosine of x is greater than or equal to 1 here. This becomes p times 1 minus 2p, and we just extract that. And we're just left with the sign. And we show that sine is less than or equal to 1, so this just becomes 1. We perform a simple integration and receive this. And now we use the fact that Vn is between n and n plus 1, so we just choose the upper limit for it, that is n plus 1. And then again, we do the same thing we did before, and we have a telescopic sum, which gives us this result. And that is less than or equal to kx times to the power of 1 over some q plus 1. Now, the last part of the proof is showing that our constant is actually some value and does not diverge. So the first thing we do is we take this integral we had before and we extract p over 1 minus p. We use a geometric series to write it as follows on this. And we have this integral 0 to infinity sine xi times cosine of n xi. So for one example, we just choose q to be 2, and we find a general method of integrating that. In order to do that, we repeatedly use the double angle formula. Sine A cosine B is 1/2 sine A plus B minus 1/2 sine A minus B. So here are just some examples of that. For n equals 0, cosine is gone. We have this simple integral. For n equals 1, we have to do it once, and we get this. N equals 2, we have to do it twice, and so we get 2 different signs. And so we have 2 different terms. And for n equals 3, we have to do it 3 times, and it's false. So there is a pattern for generating all of these different constants, which will be adding up in order to get c to the cube. For example, if we look at the 2 coefficients that will appear before every sine term, there is a general method of evaluating them. So here are the coefficients of sine for various values of n equals 1, equals 2, actually, n equals 3, and so on. And you'll notice that it is almost like a Pascal's triangle, except with some kind of annihilating barrier across which there's only zeros. Where you can see 2 is 1 plus 1, 3, 1 plus 2, 5, 3 plus 2, and so on.
The Catalan triangle. Catalan.
Sorry?
The Catalan triangle.
Oh, is that what it is?
Yeah.
Oh, so we thought of it in the following way, where we can think of it as a Pascal's triangle with one row is a generating row of ones, and one is a generating row of negative ones. And is that what a Catalan triangle is?
Yep.
Okay, yeah. And then we just take the positive elements. And so, then we can, these are, you'll see that here, actually, n to the k minus n k minus 1. And everything else is extracted from the other constants that you'll find. And this is a conversion series. And this is the integral that is well known.
Did you compute it numerically to high precision?
Yes. So now that we've done all this work, so we've proven that what the long-term behavior of the Cloitre functions are. What are they good for? Well, we began this project really not knowing why this question was even asked. So we'll see where this takes us. So we did in our research, we did find similar infinite products that look similar. For example, from Euler, we have the infinite product of cosine of x to the 2 over n, which turns out to be sine x over x. And we know that this is the characteristic function of a uniform random variable on the interval -1, 1, expressed as a Bernoulli walk with a fair coin, as flipping between 1 and -1. Another one which struck us more is this one from Morrison, where we have, instead, it's very similar to what we had for the Cloitre function for p equals 1/3, q equals 2, except 1/3 and 2/3 are interchanged, and instead of having n to the q, we have 3 to the n, and some constant at the top. And yet, just with those subtle changes, we get a very different function than what we have seen before. And we also know that this is the characteristic function of also of a uniform random variable on -1, 1, but instead expressed as a triforking walk generated with a fair die. That is, 1, 2 you increase, 3, 4 you decrease, or 5, 6 you remain in the same position. So again, also with Morrison, we also found this infinite product, cosine of 2x over 3 of them, and we also found this one, which was very important to us, the infinite product of cosine of x of them. This is actually one of our Cloitre functions, where we let p equals 1, so then this term disappears, and q is also 1.
You have a question?
Do you happen to recall why we have these silly subscripts, omega sub Cantor and omega subharmonic?
Oh, because I'll explain it. And as I said, so this is just Cloitre 1, 1, as you can see. Now, all of these are characteristic functions of some random variables. For example, this is a characteristic function of a uniform sampling on the Cantor set. Now, what we get is, for the omega harmonic, this is a random walk where we sum over a random variable, which is just a fair die, times 1 over n, which we can call omega Cloitre 1, 1. So we think maybe we can generalize this for any different values of p and q, not just 1 and 1. And if we do, we get as follows, where we have, instead of 1 over n, we have 1 over n to the q, and rp, and some other kind of random variable. Now, this is just a zeta function, Riemann zeta function, and you can see this is within this just with the random variable. So because of that, we can really think of this as, instead of Cloitre PQ, this is omega of some of zeta PQ. So then we can think of the Cloitre functions as being characteristic functions of a random Riemann zeta function. That is, random walks using the random Riemann zeta function. So to describe RP then, we need two coins instead of one. We have one fair and one unfair. The unfair coin returns 1 with probability p and 0 with probability 1 minus p. Because you can think of this as being times cosine of 0, and this is the other case. And Bn is just a fair coin of 1 and minus 1. So, for example, given a position r and at the end stage, we flip the first coin. Heads, we return 1. Tails, we return 0. If we
you
get...
still come out ahead with an unfair coin, you never lose anything.
Sorry?
You still come out ahead with an unfair coin.
Yes,
because
we
you
get...
never lose anything. So
Yes.
it's not the right correct. It's
Yeah.
0 and 1.
Yeah.
So the expectation is P. And the other one, the fair coin, you get 0.
Yeah,
so I
we
have
actually
an
we
unfair
have a
coin.
get to that.
I prefer an unfair coin.
All right. So if it tails, then the position is unchanged. It remains in the same place. If heads, then we get to flip a second coin. And it just split uniformly. Heads, we get 1. Tails, we get -1. If we get heads and heads, then the position is we add 1 over n to the cube at the end stage. If tails, then we subtract 1 over n to the cube. This is in order to get the new positions. So this is what all of these random walks look like, up to n equals 9, actually. If we did any more, this would just be a complete black band. And in the program, every step takes 3 times as long as the previous ones. We decided to cut it off. And we assemble this drawing. This is supposed to be evocative of a Galton board. And
Can you say that again?
Galton board, like where you, and we make it this way by having the vertical axis scaled by the nth partial sum of zeta of 2. Or I should say, this is for random Riemann zeta walks for p equals 1/3. P does not matter yet, just for looking at the walk, but a tree of walks we will in a moment. And for q equals 2. And you can see there is a lot of overlapping that happens. In fact, it's possible for 2 particles to cross over one another if they start here and here. They're not disconnected areas. And this is very different from like an ordinary trinary fork tree in that it does overlap. Also, we can show it's bounded, where if we roll 1 every single time, then we just get zeta of 2 as our upper bound. And if we go -1 every single time, we have negative zeta of 2. So this entire thing is, all of these endpoints of the random walks are within negative zeta of 2 and zeta of 2. So here are a few different walks that have been selected. Like you can see, we can go this way. Because we have p equals 1/3 that is expressed here, where the 2/3, they have a 2/3 chance of remaining in the same position, 1/6 of increasing and 1/6 of decreasing. And we see that here, where they tend to want to stay in the same place. But here we see something interesting, where there's actually instance of crossing over to these 2 different paths. So now that we have all these different walks, what does the distribution of the endpoints look like on this interval? And when we put this into Maple, we did all this in Maple, what I saw actually was very interesting, and it looks like this. You can see that there is a lot of structure here, instead of just being some kind of bell curve, where there's a large central peak, and then 2 sub-peaks, which represent the first choices. This is like the 0, and this is a 1, and that's a -1. But also there are sub-peaks on the sub-peaks. where that's the next choice, and so on and so on. This is for omega PCL, or omega zeta 1/3 and 2. Now we can also show what these distributions look like for different values of P and Q. For example, this is where P is 1/3 and Q is 1. That is, this is the summing over of a harmonic series with P as 1/3. And you can see we've lost this structure, seemingly, where there's only one central P. Here we just choose, this is what we had before, what Morrison had, where Cloitre 1,1 as our characteristic function, and he actually has a picture of this much better, though, in his paper. The top is just noise. And you can see it looks very bell curved. It's actually more similar to a Cauchy distribution. So this is an animation showing where P is fixed and we change Q. We grow it from 2 to 3. And you can see the effects of this is that each of the peaks become narrower. That is, that there's less movement away from the given choice. The peaks aren't growing farther apart. This is just the scaling of it. This is 1. This is 0. That's 1, and that's -1. If this were the x-axis. Now, what is much more interesting is what happens if we fix Q and change P. And this is what we get instead. So you can see that as we grow P between 1/4 and 1, if P is 1, then it's impossible for a particle to stay in the same position. And so it must increase or decrease. And that's represented by where P is 1/2, then you're equally likely to either move or stay. And as it grows, you can see that this peak immediately disappears. But now also what that means is that once P is greater than 1/2, the peak splits because it's more likely to move than to stay. And this is, you can see very clearly here. So for just typicality of random walks for any kind of random variable, for example, we have a fair coin, or it returns either 0 or 1. These are two known conditions of typicality. This is just the strong law of large numbers. And this is the weak law of large numbers. So if we have little rp to be the outcome of the random variable for a chosen random walk, then typical values of omega zeta pq must satisfy at least these three conditions. This is just from the first die, as you said, that we require for little rp that this is equal to p, and that in general this probability of this for all random walks for capital RP must be equal to 1. And this is just our Bernoulli die, similarly. And the third condition is just that all of our walks converge. Because if q equals 1, we're not guaranteed to have a convergent walk. So this is just that the sum over all this is our walk does converge to a particular point at some point. Now, there are two different variations on the zeta function, which can be written in terms of something similar to the zeta function. For example, 1 over zeta of q is the sum of the Mobius function times 1 over n to the q. And zeta of 2q over zeta of q is the sum of the Liouville function times 1 over n to the q. Now, you can see that there's some similarity with what we had before for omega pq, where we have simply a random variable here. Now, we want to know, can these two functions be typical random walks for some choice of p? So can we, in other words, can we replace the Mobius function, the Liouville function, with some rp